we're going to jump up to limits at infinity. So infinite limits are the ones that equal, like the limit goes to infinity. The y's are at infinity. Limits at infinity are where x is approaching infinity. Okay, so end behavior. When we talk about the end, I want you guys to think about those as what's happening at the right and left end. Okay, so right would be x is approaching infinity, left would be x is approaching negative infinity. The graph. I didn't space it very well. All right, so if I want to know what's happening on a graph as x approaches infinity, what I really want to do is plug in larger and larger and larger and larger values for x. Okay, so given the function 2x squared over x squared plus 4. Guys, go ahead and type those in and tell me what do I get when I plug in 10? What do I get when I plug in 100? What do I get when I plug in 1,000, etc.? Are we getting something kind of similar? Though I wrote the fractions out instead of the decimals, but my guess is we're getting something like 2 and some change, 2 just a little bit more than 2.
It's a little less than 2.
Yeah, that's what I meant. A little bit less than 2. What's going on, Maggie?
I got 25 distance.
Yeah, I got that. Yeah.
Oh, no problem. Can you guys 25? If I simplify 200 over 104, I get 25 thirteenths, and I think that works out to be 1.92.
Yeah.
And then 1.999, and 1.999, and then 1.99. So guys, just like, there's a couple of things I want us to start looking through on this. First of all, guys, what's the limit? As x is approaching infinity, what's happening to this function? It's approaching 2. Are we all comfortable with that aspect? Because the y-coordinates are getting closer and closer and closer to 2. Can we talk about y real quick? And that's kind of why I didn't simplify my fractions, because I want you guys to see this. The bigger and the bigger and the bigger I plug in for x here. Do you guys see why these are getting closer and closer and closer to 2? Because and in reality, this is 1,000,004. When it's 1,000,004, does the 4 really matter? Is it meaningful? What about here? The 4's kind of meaningful. Over here, not so much. Here, definitely not that much. So how does that operate with our equation? And I'm going to point to this one because it's the same function, but I mean this one, but I'm by 1. So the top one is a little bit unreachable for me. When we look at this function, really close, like x equals 0, that 4 is very, very important. X equals 1, very important. Okay? But for the huge values of x, that plus 4 is meaningless. You with me? And in reality, we can look at this as 2x squared over x squared. Is this okay? And it turns out that when we're talking about x equaling infinity, only those lead terms tend to be really important. Because that 4 is meaningless because I'm plugging in x equals 1,000. Is this okay? All right, so what if I plugged in, started working towards negative infinity? Is any value in this going to change if these x values became negative? Because then, 2 times negative 10 squared is going to be 2 times positive 100 still, right? So because everything's just squared here, it makes no difference whatsoever. Are we still good? Thank you. It's because Lombardi's too loud, right? She's the worst. She's the worst. I stopped counting the 9s because it's a lot of 9s, okay? So this is also equal to 2. And in fact, if we were to look at a graph of this function, you would see a graph that looks kind of like this. Where you see like most of the behavior, once we get far enough away from that y-axis, is going to stay relatively flat. It's going to be pretty darn close to 2. Okay, and it's only for those like smaller values of x that 4 ends up taking meaning. Also, there's a hole at the tip of the graph for sure. Now, we basically just came up with the definition of a horizontal asymptote. Cool? It's that as x approaches infinity, the y's are approaching a constant number, hence we can see this flat horizontal line. But only at the very far ends of the graph. We only care about the right and the left arrow of a graph. All right, so here's what I'd like you guys to do. I'd like you to calculate these foreign limits real quick. I'm anticipating you would do this graphically for now. So look at the graphs of these and find the limit as x approaches infinity, negative infinity, etc. So it's graphing the line y equals 1/4. Cool. So is this considered a horizontal asymptote, or do these graphs have horizontal asymptotes? Yeah. Yeah. So, so rational functions like this one, where it's like rational being those algebraic fractions, okay, and exponential functions are generally where we will see those horizontal asymptotes. So let's calculate. So if I ask you, what are the horizontal asymptotes of the and ask you to show analytic evidence, what I'm asking you to show is the limits. Now, there's basically one rule we follow, okay? And that is the limit as x approaches infinity of something over x, some constant over x, that is equal to 0. And everything else we're going to do, I'd like you guys to take that idea and work around it. Is everybody good? Okay. So let's look at this first one. The first thing I might try to do is factor this. If I try to factor this, if I ask you what are the horizontal asymptotes, what you need to do is take the limit as x approaches infinity of x plus 3 over x squared minus 4x minus 5. And then the limit as x approaches negative infinity of x plus 3 over x squared minus 4x plus 5. And by plus 5, I meant minus 5. If I factor this, let's see, what would we get if we factored this? Because so far when we've seen stuff like this, we've factored the denominator, yes? What do I get when I factor x squared minus 5x, minus 4x minus 5? X minus 5x plus 1. So did factoring this help us at all? Not really. Okay. So we're not going to factor it. We're going to do something else. Okay. Now, we weren't wrong to try and factor it. Trying to factor is by far the easiest way to do this. Okay? So, but instead, I'm going to do a step that at first might feel a little bit unpleasant, but I'm hoping it will make sense as to why I do it. And what I'm going to do is I'm going to multiply by 1 over x squared to both the top and the bottom. Before I explain the why, okay? Before I explain the why, let's see what happens when we do. Okay? So if I multiply the numerator by 1 over x squared, well, I'm going to get 1 over x for that first piece, right? Plus 3 over x squared. And on the bottom, I'm going to get 1 minus 4 over x minus 5 over x squared. I'm going to just let you guys absorb that for a second. Now, what we're allowed to use is the limit as x approaches infinity of some number over x. Yes? So now, as x approaches infinity of 1 over x, what is the value of that fraction equal?
0.
Plus, what about the value of this fraction? 0. What about the value of 1 is going to stay? 1. 4 over x is going to become 0 and 0. So what is that horizontal asymptote on the right here? 0. No, yeah, 0. 0 over 1, which is 0. So the idea being, like, x to the third, or x plus 3 over x squared minus 4x minus 5 is not in this form of c over x. And that's what we know is equal to 0. So what we're doing is transforming the equation into that. So and what we choose to do is we're going to divide through by whatever the highest degree term, in this case the x squared is. We're going to divide everything by that to create a fraction that is a constant over x. That's always going to be our goal. That's the analytic evidence I would want to see. Yeah.
How would we be able to do that through like the limit? Or it's not functions, but like the different properties of limits. How would we be able to do that?
So
Like how would we be able to take the limit of each part of that, I guess, fraction?
we already have been. If I asked you to take the limit as x approaches 2 of that fraction, what would you do?
What were you saying? Just point it.
You would just plug in the 2, right? But really what you're doing is taking the limit of the x.
Oh, I see.
You with me? It's the same idea. That was a great question, though. Okay.
Are we not doing approaching negative?
Yeah, we are going to do approaching negative infinity. But the nice thing about the approaching negative infinity is it's going to be the exact same thing. Because if I'm approaching negative infinity, positive infinity, the same rule applies. Okay? So my answer in this case is still 0. It's not always going to be 0, but it could be. In this case, it will be because of the type of function that we're dealing with. Yes?
Why did we multiply by 1 over x squared?
We wanted to get a bunch of pieces that look like this, because I can plug infinity into this and call it 0. Okay? I can't plug infinity, I don't know the value of doing, if I plug infinity into the top and into the bottom, okay? Maggie, let's look at them separately, okay? If I said the limit as x approaches infinity of x plus 3, you would say infinity, yes? What would you say on the bottom? Plugged in and took the limit as x approaches infinity of the denominator. You would get infinity. But this is what is infinity over infinity? Well, that kind of depends.
I just, so you're just supposed to know that, what to multiply by?
Yep.
By looking,
So what you're going to pick is the highest degree term,
because then.
because that'll take care of everything else. But you don't, you want everything to either be a whole number, like the 1. That one. Okay, so as I'm looking at this one beneath it, I'm not going to multiply by 1 over x squared. I'm going to say, well, what's my highest one? So this becomes 5 over x over 1 plus 2 over x. These two things are equivalent. And if I ask you what is the limit as x approaches infinity of 5 over x plus 2? I'm sorry. Erase that. I'm going to do this. My bad, y'all. What does the top become? The bottom? 1 plus 0. So overall the value of the fraction is 0. Likewise, if I do this one, I get 0 over 1 plus 0 is 0. Now technically, sometimes my brain This is going to make sense in just a second, okay? Sometimes my brain works faster than my mouth, okay? Technically, the question is to determine any horizontal asymptotes, which are the equation, what in this case would be y equals 0, because that's what the y is equaling. Oof. Let's do this one next. All right, so what should we multiply this one by? 1 over x cubed. And we end up with 4 minus 4 over x plus 5 over x squared minus 2 over x cubed. What do you guys think? What about the limit as x approaches negative infinity? It would be the same. So our horizontal asymptote is the line y equals 4 over 3. Are you guys watching the kids walking or the truck trying to park? There's a pretty big truck to try to park.
Yeah, I was gonna say, I think it's huge.
Okay. Can we all, real quick, you guys aren't going to like this part, and I need you to breathe with me, okay? Can we all just breathe? And I know you're not going to like it. It's going to be okay. I promise. Everybody just take a deep breath with me. Ready? Let's look at this one. The square root makes things slightly complicated. It makes it really complicated. Because, like, I want to multiply by something, but what is that something? Okay? So we're just going to breathe. This will be on the test. It's a guarantee. Okay, I'm telling you right now, it'll be there. There's at least 2 examples in that homework packet for you of this, okay? All right. Because the problem is, I'm struggling with what is the highest degree term right now. Because that x squared in an x squared, it's in that square root sign, okay? So here's what I'm going to do. I'm going to take that square root of 4x squared plus 7. And all I'm going to do is I'm going to pull the x squared out of it like this. Now, what is the square root of x squared? Kind of. It's not actually x. It is the absolute value of x. Guys, if I asked you what is negative 5 squared? And then I take the square root of that. So if I took the square root of that, I get 5. And now what is 5 squared? 25. I take the square root of that, I get 5. Everybody good? So the square root of negative 5 squared is 5.
Why are we only doing positive because it's a positive radical?
Yeah.
Okay.
But x could be positive or negative, and if x is negative, the answer is positive, and if x is positive, the answer is positive. So it's really the absolute value of whatever x is. Yeah.
Could you square the top, the numerator, and the denominator, and then multiply by 1 over x squared?
No, 'cause
So multiplying by something over something is multiplying by 1. You're not changing the value of it. So like I'm allowed to say 1/2 is equal to 2/4 because I multiplied by 2 over 2, which is 2 over 4, right? But also what's the value of 2 over 2? 1. So 1/2 is equal to 2/4 because anything times 1 is itself. Like that's that whole idea when we multiply the top and the bottom by the same thing, we aren't changing the value of it. Squaring does change the value. Like if I give you the fraction 2 over 3 and I square it, I get 4/9. So I love that you want to try that. The difference between multiplying the top and the bottom by the same thing is I'm just multiplying by 1. It keeps its own value. Did that answer that question? Yeah.
I know this isn't helpful for what we're doing, but if in theory you wanted to square it, would you square the f of x too?
Yeah, and then it's just going to start feeling icky because then you'd that's not a good idea. And the positive negative squaring creates extra solutions. That makes it a bad idea. All right. Okay. That's our first deep breath. Is our first deep breath okay? All right. Now I can multiply the top and the bottom. My highest degree term is x to the 1 power. I'm going to multiply by 1 over x over 1 over x. And I get the absolute value of x over x times the square root of 4 plus 7 over x squared. And then on the bottom I have 1 plus 7 over x.
Why is the radical not divided by x?
Because it's like because this is just something times something, right? And so I'm just
Gotcha.
okay. Okay. This looks icky, doesn't it? Believe it or not, we're done like rewriting the f of x. So now we're just going to take the two limits as x is approaching infinity and as x is approaching negative infinity. So the limit as x approaches infinity of this big thing, we have absolute value of x over x. All right, so this is what we're trying to take.
The denominator is 1.
So the denominator is 1 plus 0. Everybody good with that? What about the radical?
It's 2.
Well, for right now, I'm going to leave it as 4 plus 0, but it will be a 2. Yeah. So really, as we think about this, by doing what we've done, all we have to think through here now is the absolute value of x over x. So as I start plugging in numbers, really, really big numbers for x, what's going to happen to the value of this fraction?
It's gonna stay at 1.
It's going to stay at 1. Because they're going to be the exact same two numbers, right? If it's positive, I think its absolute value, it's going to stay x over x. Something divided by itself is 1. So if I ask you guys to simplify this fraction, it works out to be 2.
Why are you allowed to plug in like basically infinity over infinity and call it 1, but you have to do all of this when you plug in infinity?
That's an awesome question. If this was it has to do with the fact that this is in fact the exact same number,
Okay.
right? Like x and x are the same. X plus 2 over x squared plus 5x plus 3 don't always have the same value. These two will in fact always have the same value. Is that okay? All right. Will this change if x is approaching negative infinity?
Yes.
I'll still have my 1 plus 0. Okay. Are you guys cool with me saying this will still be the square root of 4 plus 0? All right. What's going to happen to this square root x, or I'm sorry, this absolute value of x over x?
Negative on the denominator.
Say that again.
Negative in the denominator.
Positive in the numerator.
Yeah.
Negative and positive are the exact same number. So this is going to equal
Negative.
-1. And overall, this limit is equal to -2. So this function has 2 horizontal asymptotes depending on which side we're looking at. Okay, so y equals 2 as x approaches positive infinity, and y equals -2 as x approaches negative infinity.